Okay. Hello, everyone. Let's get started with lecture 9 in the Advanced Introduction to Machine Learning course. So today, last time we looked at k-means and k-means plus plus. We said that k-means is one of the most basic and foundational clustering algorithms, and it's based on Euclidean distance. And we also said that it has the solution heavily depends on the starting point. So if the starting point is not initialized right, then you may not end up with a good clustering. So k-means plus plus fixes the starting point issue, right? So it uses a better initialization. Once it does the initialization, it continues with k-means. So k-means plus plus is just a better initialization plus k-means, which already we looked at. But both k-means and k-means plus plus yield spherical clusters. So if your clusters are not spherical, they're spiral in nature, or there is some other pattern that is present in the data that you want to capture that's not spherical, then k-means is not the best method for clustering. And we also spoke about we'll spoke about it a little bit, how to choose the number of clusters, right? So if we had a supervised learning algorithm, you would do hyperparameter tuning, right? It'd say, okay, let number of clusters be a hyperparameter. We will tune for it, and we'll see if we can get a good number. But here we don't have label data. So because we don't have label data, it's like you don't know how to tune a number of clusters without any validation, right? So that's something that if you have some prior knowledge, you can incorporate. If you know you're looking at clusters of some species or subspecies, or you expect a certain number of clusters, then that could be K, right? Some prior knowledge. So you can have one prior knowledge that informs this, for example, number of species or subspecies of, let's say, whales. Okay, and you have some data from there. You expect a certain number of subspecies, so you want to try out different number of clusters. Maybe you say, okay, let's try 5, let's try 6. Does it make sense? So that can be one. People use some other thumb rules, but they're not very well grounded. Like there's something called the elbow method with number of clusters, and you look at the intra distance and inter distance between clusters, and then that might be a way to pick the number of clusters. I think there's inter cluster distance. So you want this to be large, and then intra cluster distance. You want this to be small. So then you can say, well, your clusters are well defined, because if the intercluster distance is small, that means you have two clusters that are very close to each other. Maybe they could be combined into one. If your intra-cluster distance is too large, that means you have a really big cluster. Within a cluster, there's a lot of distance. Maybe you can actually split it. So when one is higher or lower, you can say, maybe I need to merge or I need to split. So that's kind of the intuition with using these metrics to determine the number of clusters. But once you pick the number of clusters, K, then it's also a matter of initialization. So let's say you do k-means plus plus. The only hyperparameter for k-means plus plus would be number of clusters, right? Because it does the initialization, it will do the A step and a C step. We discussed, like there's the assign step, and then there's the centroid computation step. So A and C. And we also went into the computational complexity of doing the A step and C step last time. And we also discussed the applications of clustering. One instance is outlier detection, anomaly detection. So it's an example. Let's just write it down here. Outlier, anomaly detection. Like if you know my data is good right now, you can cluster it. And then when you get new data points, you can see if they fit in one of the clusters. If they don't, maybe it's an outlier, right? And this can apply to anything like fraud transactions. It could be outliers in your metrics that you're using to track your software or your model, right? You have some metrics, some latency, something, this thing, that thing, or you're looking at KPIs. That may be something you can look at. How are the KPIs doing right now? How are the KPIs doing in a month? Is there some outlier? And so it's probably easier once you do clustering to identify which of them, maybe this month there is some outlier, and you're like, that can set off an investigation in your business to see what actually went wrong, right? Like for example, if you're working with cloud computing and cloud infra, you need to really monitor APIs because there's a lot of things that can go wrong, and catching it early is the key, right? I think there are some folks here who work in the cloud infra space. So if you have some insights, feel free to pitch in there. But so that's another, right? So cloud infra monitoring. So a lot of monitoring systems usually have outlier detection of some kind. It can be something really simple or something more sophisticated. But the more sensitive these things are, the more you want to invest in sophistication if it really helps you catch things proactively. I think people are even like you can even preempt things, like you can monitor the temperature, you can monitor certain parameters of servers, so you know when a server is going to likely fail before even it fails. So instead of waiting for some outage to happen, you can actually set up monitoring so you can preempt and proactively detect and resolve things as they come up. So these are other applications. And obviously we also spoke about clustering can help with finding representatives, right? I think we spoke about representative embeddings. Like you don't want to store embeddings for every single customer or every single product, but you find representatives, and then those can help you make recommendations. Does someone have a question? Right. Okay, so today we'll look more into clustering, and we'll also look into data visualization. And so there's something called TSNE. We'll look at this very interesting use case for data visualization. So just some more summary. I think we already discussed, but let's just go through the slide. K-means is a generic clustering algorithm that can take n data points and group them into K clusters based on Euclidean distance. Clusters make sense if the Euclidean distance we're using makes sense, right? So the K-means make sense if you're good on Euclidean distance. We looked at the computational complexity for C step and A step. Yeah. So we'll look at this counter examples, like we have spiral clusters or something that cannot be detected by K-means. So we'll look at agglomerative clustering today, which can actually do the job. K-means plus. Yeah. So this is something we'll focus on in this talk, agglomerative clustering, to resolve the issues that K-means has with spherical clusters. Right? Okay, so let's look at clustering points in 2 dimensions. So if you look at K-means or any of these algorithms for clustering, the data itself doesn't have to be in a low dimensional space. It can be in a high dimensional space. All you need is a distance to measure how far 2 points are from each other. but you don't need it to be in 2 dimensions, right? But the thing we're going to discuss, which is TSNE, is data visualization method, especially for clusters, but in 2 dimensions. So no matter how high dimensional your data set is, you kind of boil it down to 2 dimensions. So if you want to talk about it, it's easy to display it in 2 dimensions, and then you say, hey, here's a graph. Here are my 6 different clusters. And I think there's something going on here, there's something going on there. So you want to brainstorm what is happening with your data set in 2 dimensions, let's say with your manager or with your colleague, or on a project. It's easy to have something in 2 dimensions and you can talk about it. So this TSNE method is pretty effective in this use case, in this scenario. Okay, let's take a look at that. So like we spoke about last time, one use case is images. Let's say you have 1,000 images and you want to cluster them onto a super grid, so that images that are closely placed on the supergrid are similar, and the images that are further away on the supergrid are dissimilar. So k-means clustering will not really get us to solve this problem, because like, what are you going to do? We're going to put each image in its own cluster. How are we going to place it in this supergrid? It's a little bit ambiguous to know how k-means will help, right? So this is something you can call this soft clustering, because it's not exact clustering, but you're saying any part of the supergrid will look similar, right? Different parts of the supergrid will convey different kinds of images. So there is a clustering going on, but it's soft. It's not exact. It's not like, okay, there's 5 clusters, is because it's a supergrid, right? So suppose you have a supergrid that looks like this. So I don't know how many images are there here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So number of rows here is 12. How many columns do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So this right here, this supergrid has 240 images, right? If you take a look at the supergrid, it's constructed based on an algorithm, right? So no one actually patched it up in this way. It just was made through an algorithm. So if you take a look, let's look at the bottom left. You see a lot of flowers, right? And then from flowers, we start to transition into fruits, right? And then from fruits, you transition into veggies. There's like veggies here. And from veggies, you go into noodles. And then, so it's still all food. But then you start going into crockery. And then somewhere this circular thing becomes baseball. And from baseball, you go into wheels. And then you can keep going this way. These are still wheels. And then it becomes equipment. So then it becomes knife. So you can see this is not related to shoes. Like, knife is not related to shoes, but you look at the structure or the shape, it's kind of like there's this kind of long kind of setup. So maybe you transition to shoes here, and then this goes into baseball bats. It's very interesting how there is some structural similarity in the images just from the data. Just by looking at the image, you can say, oh, this is structurally similar. But if you ask someone, is knife similar to shoes, you'll say no. But the shape of it, you see this is matching the shape. There's some soft similarity of the shapes that's being matched here. And then you go to the bottom right, it's all dogs and wolves, and then there's birds here. You go to the middle, there's birds, and then it just keeps going on, right? And somewhere you start seeing people. That's interesting. So you see from here to here, this is like an angled baseball bat or something, right? Or this is a hockey stick. Yeah, it's a hockey stick. So this is an angled. This is like a knee, right? So knee brace and knee, and it's angled, and from there you go into people. So start going into people, and then all of that. Very interesting. So the t-SNE method, so t-SNE stands for T-stochastic neighborhood embeddings, is a it's specifically a data visualization. And you can see, like, for images, it's super helpful. You want to construct a super grid, a collage, automated collage, you can say, of images in a way that it makes sense and they're all connected. This would help you do that. So it's specifically used for data visualization, and it's able to give you two-dimensional embedding. So each of these images may have a very high representation, right? Like an image is, if you take a raw image, any of these images would be like what, 100 by 100 pixels, maybe even more, like 200 by 200 pixels. So there's a lot of raw information in there, right? 100 by 100 is like a 10,000 dimensional vector. If you think of it as a vector, this is the same as like 10 to the 3, 10,000. So 10 to the 4 dimensional vector. But you take this 10 to the 4 dimensions and then you bring it down to 2 dimensions. So that's t-SNE for every single image. So you take these 10,000 pixels and say, okay, can I compress it to a point in the space so I can put this image in here? Can I say this is more on the left, this is more on the right, this is more in the center? So that's what t-SNE will help you do, is compress it in a way that it makes sense. And we looked at images, but you can apply this to other use cases, right? You can have, you want to understand words and how words relate to each other. How do words, if you want to take a set of words and put it on a graph, how can you differentiate them? Will it be more on the left? Will it be more on the right? How do you see that process? So that's something that you can also use a t-SNE for. There's multiple applications of t-SNE, so we'll look at some of them in a bit. Okay, so SNE, SNE stands for Stochastic Neighborhood Embedding. So the high-level idea is you take images or words or any set of data, and that could be in high dimension, but put it down to 2 dimensions, so that objects that are similar are placed in the same area of the grid, and objects that are farther from each other are in different parts of the grid, right? So there's 3 things here. So let's just parse this. So embedding. So whenever you hear the word embedding, like in this, in this class or in other classes, just imagine a vector, right, of certain dimensions. So maybe this is in 128 or in 256 dimensions, or in this case, in the specific case of t-SNE, an embedding is just some XY coordinate. So it's in 2 dimensions, right? So it's just a lower dimensional representation of a data point. Even if the data point had 100,000 dimensions or 10,000 dimensions, you're compressing it into a smaller dimensional space. And that the dimension of that space that's something that you determine, but typically it's not more than 1,000 dimensions. For t-SNE, it's just 2 dimensions. So you're putting it all in 2 dimensions. The t-SNE is a special case. So whenever you hear the word embedding, just think of this small dimensional vector, right? Irrespective of how many dimensions your original representation has. For instance, if you look at the bag of words model, if you have a vocabulary size of 200,000, right? Your dictionary has 200,000 words. Any sentence, if you want to represent in bag of words, would have a dimension of 200,000. Would you agree? Because you're going to put ones for the words that are present in the vocabulary and zeros for the rest. So in a naive representation, you will have a 200,000 dimensional vector. But even once you apply an embedding to it, you're applying embedding, you take all of that and compress it to 128 dimensions. And each dimension captures some relevant aspect of a word. Like, is it a verb? Is it a noun? Is it pertaining to this kind of an object or that, or etc. So there could be multiple dimensions that explain what a word, what this word means, right? So that's an embedding. So that's one. And then we have neighborhood. Neighborhood is like, as it makes sense, you're trying to map one image to the other, or you're saying, given this image, what are other images that are similar to this? So you're understanding the neighborhood of the images and how this image relates to other images. And then the stochastic part, obviously, we have seen enough of this. There's randomness in the algorithm. So it's a stochastic neighborhood embedding. So there's going to be some randomness. So that means every time you run this t-SNE or stochastic neighborhood embedding algorithm, you may get a different result, right? So it's just like stochastic gradient descent. It's gradient descent, but it's stochastic. There's randomness there. So this is a algorithm or a method that can give you an embedding based on neighborhoods, and it's random in nature, right? So that's stochastic neighborhood embedding. Okay, so as we said, there is soft clustering going on here. We've looked at clustering. We said, okay, clustering is easy. There's like 5 groups of objects. So there's 10 groups of objects. You determine what that is, and then that's clustering. You can say clustering in that sense is kind of exact or hard. This is soft clustering, which is like, yeah, well, this object is connected to these groups of objects, and then you can keep saying the same thing for as many objects as you want. So there is a soft clustering, there's a neighborhood that kind of determines the soft clustering, right? The neighborhood effect is present. So if you look at the supergrid and you say, let's focus on any neighborhood, that neighborhood will be similar in nature, right? So you can like zoom in on any parts of this. Like you can say, let's zoom in here, and then you'll see dogs, right? Or you can say, let's zoom in here, and then you see flowers. Let's zoom in somewhere place. Let's try. Let's zoom in here, and you see people. Okay, so it's up to you how you want to zoom in. You can zoom in as much as you want or less, but you'll see typically there's some relationship there. So there is like lots of clusters in some sense. So soft clustering is saying you can form as many clusters as you want, but here's how I'm arranging it, right? And there's a neighborhood effect in place. Okay, so how does stochastic neighborhood embedding work, right? So it has a similarity measure, and it defines a probability. So PJI is probability of let's say J being close to I, right? So we'll use this notation PJI, PJ given I. So you can say this is probability of J given I. So Pj given I is something that you define as a probability. So here we're using the Gaussian distribution to define the probability. So if you see this e to the negative x square or 2 sigma square, this one, you might also see 1 over square root 2 pi. This is the probability density function for a normal distribution, right? So in some sense, you're using the Gaussian distribution to inform you of how to define the probability, right? So but what's sitting inside the Gaussian distribution? You see there's a Euclidean distance sitting here, right? So essentially what this probability is doing, Pj given I is doing, is it's saying, let's compute the Euclidean distance between any 2 points, okay? So distance is the opposite of similarity, right? Distance is how far 2 points are from each other. Similarity is how close 2 points are to each other. So how do you get a similarity from distance? Well, you can just take the negative of the distance, right? The larger the distance, if you negative exponentiate it, the smaller the distance will be, right? So negative exponentiation of something large gives you something small, right? So e to the negative 10 is like close to 0. E to the negative 1 is whatever, like something, like, I don't know what this number is. Or let's say e to the negative 0 is 1. So the larger the distance, when you negative exponentiate it, you get something really small. Or in other words, the smaller the distance, the closer the 2 points are to each other, negative exponentiation will give you something bigger. So the probability becomes high. And this is a probability distribution. Why? Because you're normalizing it by the summation in the bottom. So when you sum up all the j's given an I, you will get 1. So that's why pj given I defines a probability, right? So you can think of it this way, given an image, what are other images that are closer to this one, right? So the ones that have a higher probability, for those j's, you'll say those j's are closer to this image. The ones that have a lower probability, you'll say those are farther away from this image, right? So this is a way of defining similarity based on Euclidean distance through the process of negative exponentiation. And this is also connected to the Gaussian kernel. So the Gaussian distribution also has this property, e to the negative x squared over some 2 sigma squared, right? So that's what we see here. So what we can do is, if you have n images, you can form all these pairs, n square pairs, and compute this, define this probability, right? So what the stochastic neighborhood embedding does is, this similarity is defined in, so these xi and xj live in probably high dimensions, right? They don't have to be in a small dimension. But what they do is you define something q, which is another distribution, where yi and yj are in 2 dimensions. So essentially, you're taking something that is really big. Let's say this is 1000-dimensional vector, and then you're moving this into something that looks like this, where this is yi, which belongs to 2 dimensions. So stochastic neighborhood embedding is taking the original vector xi and compressing it into 2 dimensions, right? So this is the SNE that is doing this job. How is it doing it? It's constructing a proxy distribution. So you can say this Q is a proxy distribution, which is again saying, how do 2 images relate to each other? How are the probabilities of, like, given image I, is image J close to it or not? So it's constructing a proxy distribution by replacing the xi with the yi, right? So you're replacing xi and xj with yi and yj. Now, what you'll do is you will learn these yi's and yj's. That's essentially what SNE is doing. It's saying, I will learn it by having a loss function that will make the q close to the p. If I make the q close to the p, then whatever behavior I observe in this high dimensional space with the xi's and xj's, I will observe the same behavior, hopefully close enough, in the low dimensional space. So then I am able to preserve that probability as I embed these points from a higher dimensional space to a low dimensional space. So you can embed in any way, right? You can just say, take a point and then say its embedding is 0, 0 or 0, 1, and I'm done. But that's not a useful embedding. It's going to put everything to 0, 1 or 0, 0. Or you can just say, let's randomly assign 2 numbers for every single point. Like for every image, I'll say, okay, pick 2 random numbers, that's my embedding. But that's not useful. What information is that conveying? But when you have some preservation of property, in this case, preservation of similarities between images in a low dimensional setting, then your embedding is actually useful. You can use it to visualize, you can use it to understand, you can use it to clusters, do soft clustering like we discussed. So that's what is going on here. And if you're interested in more details, you can take a look at the paper on TSNE. It has more on this, but this is the essential idea, right? So let's take an example. So let's say you have the MNIST digits data set. So this is, how many of us have looked at this data set before or worked with it before? Okay, I see a couple of hands. So this is one of the most classical, you can say, multi-class classification data set that people have thrown tons of algorithms on over decades, right? This has been really, really tested to the limits. It's not a really big data set, but it was pretty good in the sense that one of the motivations for AI was handwriting recognition, right? So these are handwritten digits. So if you can solve this, you can write a digit in any way like a human would do it, and you can an algorithm looks at it and says, ah, that's a 1, that's a 2, that's a 3. Then you've kind of solved the classic problem that people were really interested in. One is face recognition, one is digits recognition, one is handwriting recognition. So this is focusing on like specifically handwritten digit recognition. So this is a very classic problem. So, and associated with that is the MNIST digits data set. So people have really tried a lot of algorithms on this. So here you can say the label for all of these data points is 0, the label for all of these data points is 1, the label is 2, the label is 3, and so on. This is your Y, right? And this is your X. This is X1, X, whatever, XK, XK plus 1, and so on, right? So each, and what is this X? It's X is an image. It's an image of a handwritten digit. So the image is your input, but your label is a number. It's like 0 or 1 or 2 or 3 or 9, right? So these are, we just want to make sure we get the representation here. The input is an image, but the output is a number, right? So people have also applied, so let's say you want to understand this data. Okay, sure. I know with MNIST you have labels. So these are in your training data, you will have labels. You can build a multi-class classification algorithm. Let's say you tried random forest. You would say, okay, pass in an image, random forest does its thing, and it says, okay, here's a 1. I think it's a 1, or I think it's a 2. Or you can apply logistic regression and you can do multi-class classification, and you'll be able to figure out, you'll get some accuracy with it, right? But let's say you did clustering, or you wanted to do dimensionality reduction. Let's say, oh, these images are too big. There's like 100 by 100, 10,000 dimensions. Let's compress it. So there's a couple of ways we can actually do compression. One is called PCA. PCA stands for Principal Component Analysis. So PCA is a classical method from statistics that is able to identify the directions in the data of maximum variance, right? So that's how it came about. But you can say it's trying to understand the variance in the data, and that variance, like in certain directions, the variance can be higher. For instance, if you take a look at this data, and let's say this is your data, this is X1, X2. Then PCA would say, well, you know what? This direction has a lot of variance. Okay, so I'm going to call this principal component 1. And then the orthogonal direction to that is this. That's going to be my principal component 2. So PCA is based on understanding how the data is shaped up in not just 2 dimensions, but hundreds of dimensions, and identifying which is that direction in which I see a lot of variation in the data set, right? Like you can see here, this dimension has a lot of variation. There's a lot of variance in this direction. So understanding, so you're essentially understanding the shape of the distribution, you can say. You're understanding where there is variance. And understanding the variance can help, because when you have variance, that is when maybe you can probably have different predictions, right? Like if there is no variance in dimension, it's all the same, then maybe that's not really predictive. Does that make sense? Like when you have some, like, let's say you want to predict, the housing price from like the features that we have. And we looked at this example. Let's say one of the features is, does the neighborhood have a park? Almost every neighborhood is going to have a park, right? So where is the variance in that feature? There's not much variance. So is that a useful thing to know, if there's a park in the neighborhood, for predicting the price of a home? For most neighborhoods, you would say not really, because every neighborhood has a park. So like, especially in a place like Seattle, you have like more than 500 parks. Like you can just walk to a park from your home, literally, in many, many places. So having a park in the neighborhood, that's not really predictive. So you can say that's a dimension, or that's a direction in which there's no variance. So if you did principal component, that might come up as principal component number 50. no variance. And that's not really helping me make predictions. So what that tells us is where there is variance in the data, a good amount of variance, maybe that's where the insight lies. For instance, for the same example of housing price, if you look at square footage, is there variance in square footage as you go across different homes? Yeah, we do see a lot of variance, right? So perhaps square footage is an indication of price. We don't know that, but because we don't have labels here, we're just doing variance analysis on the data. There is some variance going on in the square footage. So maybe that's helping me predict. So principal component analysis is based on analyzing the variance in the data and with an assumption that the directions of the data in which you have variance have some information there in terms of prediction. So if you did PCA on these images, and then you were to plot the first and second principal component, it's all meshed up. So you can say, okay, the purple ones seem to be different from the yellow ones, or they kind of separate, but then there's a lot of overlap. So you're not able to say, okay, the zeros look different from the ones, look different from the twos. It's all kind of meshed up here. So there is variance in, both the components, and it's not really indicative of like the kinds of variance that you expect is not helping you visualize these digits properly or differentiate these digits, right? So the PCA as a method for data visualization is not usually very useful. Okay, you can get two principal components, but it's not really helping. But if you did t-SNE, you see now that the digits actually separate out in two dimensions. Like even if I had no idea of what the blue points are or what the green points are, right? So here the blue points represent 6, right? And the green points represent 3. So let's say I didn't even know this. I didn't know that these points actually represent the digits 6 or digits 3. I can still say that, there is a reason they are separating into different clusters. They must be representing different things. So that is useful to get from t-SNE as compared to PCA that we just looked at. So t-SNE as a data visualization is much more useful than principal components, for instance. PCA is helpful to do dimensionality reduction. So if you don't want to do data visualization, you want to just reduce the dimensionality, you can just pick the top. People typically pick the top 10 components. Okay, let's look at the top 10 directions in which there is variance in the data. That should help me understand the types of data I have. So PCA is helpful for dimensionality reduction, not necessarily to 2 dimensions, but t-SNE specifically, as you can see here on the MNIST digits data set, it's able to separate out almost all the digits into their own space, right? And this is learned automatically from the model. The model is actually putting everything in their own different space. You're not even, you're not telling which is which, right? So that's that's where t-SNE stands out. And so people have tried data visualization in 2 dimensions, and it was not really working so well. But then when they came with t-SNE, the t-SNE folks showed that on many different data sets, you can actually get cool visualizations happening in 2 dimensions for most data sets. And there's a lot of hyperparameter settings that can help you tweak things. So if you're not getting it here, you can get it there. So those are some things you can also take a look. I think it'll be part of your next assignment to use t-SNE. So you can explore t-SNE on different data sets. So let's look at a little bit of the math and the loss function bit here. So, loss function for regression, like we said, this was, what was this? Quadratic, right? So you have quadratic loss function. Loss function for classification. What is this? If anyone remembers. Cross entropy, right? So you remember the summation pi log yi log y hat I. So you're looking at how the y hat distribution, is it close to the yi distribution? because your classification produces a y hat vector, which is one hot, not one hot encoding. It's a probability, right? You get a probability distribution across classes. So you're trying to match that probability distribution against this. So tsne also does something similar. It is doing some kind of entropy, but it's something called KL divergence. So the loss function for tsne, and the reason it's doing something similar is it's also dealing with probabilities. If you remember, we're looking at a proxy probability distribution Q that matches or preserves the properties that you see in the P distribution, which is in the original data space. So whatever similarities and distances that you have between images, you want to preserve in the lower dimension, and you want to make sure that the P's and the Q's match up. So here, it's kind of close to this, and it's called KL divergence. So this is the loss function for this, and it's close to this. Right? So if you see how it's close, actually, if you remove the pi here in the numerator, and you just replace it with 1, then you get the cross entropy. So it's just adding this extra layer. But also it turns out that this function is non-negative. So it's actually a distance measure. Let's say it's a distance measure. So if KL divergence is 0, that means P and Q are exactly the same, right? So if KL of PQ equals 0, this implies P and Q are the same. So if KL of PQ is large, this implies P and Q are very different. So we have a distance, and we would like P and Q to be same. So that makes scale a nice candidate for a loss function. Because when you minimize scale, you're trying to bring P and Q to be close to each other. Right? So the P and Q distribution to be close to each other. So so the tsne uses the KL divergence as a loss function. Yeah. So if you want to elaborate, it looks like this. Across all the data points, you sum up or you average, let's say you average the KL distance between Pi and Qi, and you minimize this for the Q, which has Y's in it, then you basically minimize the loss function and you obtain the set of two-dimensional embeddings. So when I minimize this, obtain two-dimensional embeddings through tsne. Okay. All right, so you can take gradients and you can do gradient descent and all of that. So I'm skipping this part, but feel free to take a look. So what we'll do now is we'll do a quick breakout. This is something that'll be part of your next assignment, maybe the conceptual assignment. And you can create a YouTube video as a part of this assignment. So this will actually be, you'll upload it on YouTube, you can share it on Discord. But in the process of making this video, you can think about what choices I made to group these images together are giving me this kind of a video, right? And then you can backtrack, you can change something. Maybe let's say what Ozzy was sharing about clustering. Maybe I choose 2 clusters and now I choose 10 clusters. I get a very different video because it's able to jump between clusters in a different way. Or I didn't do clustering, I did something else and I was walking through the grid, I did some random walk and I got a different video. So it'll be a very creative and also iterative process of understanding the tools that we're using to create the video and also seeing what the result is, right? And some people were also asking me last time, how do we share our work better? So if this is something you want to share on LinkedIn, feel free to go ahead, but definitely put it on YouTube. And maybe we'll also share it on the Discord group so we can see each other's videos. And you can pick any set of images, right? You can pick the image flowers data set. There's something called fashion MNIST. Maybe we'll look at it today. So you can look at the fashion data set. You can look at any set of images that kind of are in a cohesive group. But there's also variety in that, right? So you want to have some variety, but also there's belong to some category. And then just throw a bunch of, you need enough images to create a video. So let's say at least 1,000 or more, and just create a video at a certain rate and then see how that video actually shows up. Maybe you guys have seen some YouTube videos, right? Where there's a time lapse or something, and then there's like things that change, but that's already in a specific area. So it's all connected and it makes a lot of sense. Here we are chaining images from some data set. And so we're trying to find the best possible way to chain it so it actually makes sense, or it's nice to watch. Okay. So that can be part of your next assignment, and I'll be excited to see your YouTube videos as you post it on Discord as well. So let's take a 5-minute break, then we'll come back to finish the rest of the lecture. Yeah, so image chaining is like we said, it helps you create a video, and this is a 2-dimensional chaining, right? You're chaining in both the X direction and the Y direction, and to see if you can chain in a way that makes sense. So this is also something that can be done, right? And not just 1-dimensional chaining, you can do 2-dimensional chaining as well. Let's take a look at some examples of notebooks on this, and I've referenced them, so you can also take a look. Let me just stop sharing here. So this is visualizing word vectors using t-SNE, right? So you may have a data set that has a set of sentences, and then from those sentences you get words, and for those words you want to visualize, right? So you're not visualizing all the words, but words that are present in those sentences and those documents, right? So there is, they use something called the word-to-vec model, which we haven't covered yet, but word-to-vec model is, we'll probably cover it maybe in this next lecture or when we get to the natural language processing part of the course. But word-to-vec is essentially a way to embed words in, let's say, 128 or 256 dimensions. So how do you get embeddings for words? The idea is that if two words co-occur very often, then they are related. So if you can use this idea to train a model to generate similar embeddings for words that co-occur, and words that don't co-occur, you're like, they must be different, right? So in some sense, this is self-supervised learning. If you heard of, like we've talked about supervised learning, unsupervised learning, there is semi-supervised learning, and then there is self-supervised learning. A lot of natural language processing can happen through self-supervision because there is some kind of information already present in the sentence structure, right? So co-occurrence, for instance, is one example. If two words co-occur, they must be somehow related. I keep seeing the same kind of associations in the sentences, they must be related. So using that information, you can train a model. And that is the supervision, which is coming from the data set itself. You're not providing any labels. So word2vec is one such model that helps you get some semantic understanding of words. How do words relate to each other? And why are certain words similar? Why are certain words not similar? This is learned in a self-supervised way. We'll go more into the details of it. It's a really fascinating topic. So this notebook uses word2vec, which is based on this idea of self-supervised learning. And it also uses t-SNE. So you have t-SNE representation of the word2vec embeddings, right? So you have to start with some representation of a word. Instead of a bag of words model, we know that's going to be very inefficient. We'll use word2vec. So word2vec is going to give you 128, 256 dimensional or 512 dimensional vectors, where the dimensions represent something that is meaningful. You don't know what those dimensions are beforehand, but you can inspect and understand, oh, this must represent the parts of speech. This must represent association with certain category. This must represent, is it an animal? Is it a human? So each dimension might represent something. And that makes up those 128 dimensions. But you don't know that beforehand. Afterwards, you kind of can inspect and understand. So yeah, so let's kind of take a look at it. So you see gensim from gensim.models import. So gensim is, you can also import glove, which is another word2vec style embedding. So it gives you embeddings for words. There's NLTK imports, there's pandas, NumPy, regular expressions, scikit-learn. So from scikit-learn, you're importing tsni. And for plotting, you use matplotlib. And this line, as we discussed, this matplotlib line helps you display images in a notebook, right? So it's important to have this. Okay, so we load some data. And then there is cleaning the data, cleaning the sentences, stop words removal. I think you might have done this for the spam classification assignment, but there's some stop words that are not really useful from this data set to visualize. Like, I don't want to visualize the, a, and, like, those are not really useful words to visualize. So let's kind of remove those. So that's what this is doing. And maybe you have a data frame and you look at this, let's say, best way digital marketing. So there's like different inspiring start stories and relationships and everything. So you get important words from this corpus of sentences. And then those are the words you want to visualize on a two-dimensional grid. Okay. So build a corpus. So you extract the words out of the sentences. So that's what this is, breaking it up into words. And then word2vec is taking any word and then saying, give me some dimensional representation. So here, what is this dimension here? So it's 1, 2, 3, 4, 5. Is it 100 dimensional? I think so. Size equals 100. So this is 100 dimensional representation of, so here, let's say I want to get the representation for Trump. You get a 100 dimensional vector for Trump. So you can get a 100 dimensional vector for anything. And it will have maybe some activations for politics, some activations for, government and things like that in this 100 dimensions. Okay. So then you also have tsni plots. So as we said, tsni can actually embed it in any dimension, but typically 2 dimensions for visualization. So you can see here, the n components is 2, means you are taking this 100 dimensional vector, which is what you start off for the words, and put it down to 2 dimensions, right? And there's some other hyperparameters like number of iterations and random state and perplexity. Perplexity is another thing you can play around with in your assignment, where the higher the perplexity, the more separated these clusters will be, and the more closer they are. So that's something that you can take a look at. So yeah, X and Y represent the 2 dimensions, and the labels represent what the word actually is, right? So let's say we did a scatter plot with X and Y. At X and Y coordinate, you have a point, right? What is that X and Y coordinate? That's the tsni representation. Tsni gives you 2 dimensions. So the first dimension is X, the second dimension is Y. So X and Y helps me plot words, but I need to annotate it, and that's what's happening here. So you annotate it with the actual, what is X of I? What is I? I is the ith word. What is that word? It's label of I. So label of I gives you the word, X of I, Y of I gives you the coordinate. Together, you can map a coordinate to a word, and then you can get a word cloud. I guess you can call this a word cloud that is based on tsni, where any part of the, you can just focus on any part of this, and you'll see there's similarity. Like for instance, on this side, if I zoom in here, I see download music, games, Windows, websites. It's all related to websites and doing something online, right? And then as you keep moving, you move towards iPhone. Now you're going towards devices and phone number, and there's WhatsApp, right? So phone number, WhatsApp, account, Facebook, profile, post. So you can keep walking through this, and you will go through different topics, and suddenly you end up in people, and then there's like other things, and then there's relationship here, friends, girlfriend, relationship, woman, feel, and then there's other things. So you can keep going. It's like you keep walking into different topics as you walk through this word cloud. You're jumping onto different topics, but in a smooth way, right? So like, again, as we said, this transition is kind of smooth. It's not like very jumpy, and it makes sense. So this is purely based on tsni, right? This word cloud representation that we just saw here. You start with an initial representation from word2vec, but you apply tsni, like we said, the P and Q probabilities. The Q probability And then we learn the y vector, which is giving you the 2 dimensions, and then plot it, and this is what you get. Is there anything more here? Yeah, you can do other things with this, right? Let's say you want to find the most similar word to Trump. So here Trump is, if you remember the queue of I given j that we saw in the lecture slides, the j here would be Trump. The I would be all the other words for which the Q of I given J probability is high. So these are all the I's, right? Trump's, Hillary, President, Bill, Obama, election, vote, Clinton, so on. And you can see the probabilities are sorted, so from the highest to the lowest. So the I given J, you can use that to search and sort. So Q of I given J gives you a probability distribution. So you can sort it based on the highest to the lowest probability and pick the top 10. The top 10 will be the top 10 most similar words to the given word J, which is in this case Trump. Right, so that's how you would apply the math that we looked at in the lecture slides. The math gets applied in that way here. Most similar word to the universe, and then the zero created vacuum space. Wow, this is very interesting, right? So you can see these the 2-dimensional representations do have some information that they're putting things together in this way. So this is one example. Let's see if we have another example. Not this one. This one? No. This one. Okay, let's see. So I want to look at another application. So this is the fashion MNIST dataset. So MNIST has been a popular dataset, but people also start looking at fashion images and making predictions classification based on the fashion image dataset. So you can get from sklearn import datasets. So this is part of scikit-learn, and from datasets you fetch the fashion MNIST dataset, right? And you get the features and the target. So X and Y from the dataset, X is features, Y is target. And then you convert the target to int type. Okay, so sample image, maybe this is some kind of a dress or a t-shirt, right? In a very low resolution version of a t-shirt, right? So that's something that you see here. And then let's say these images are still in some dimension, right? So maybe 25 by 25 is what 600, 700 dimensions. So you can still take a 700 dimensional vector. So here the pixel values give you 700 dimensions. So now t-SNE will take these 700 dimensions and put it down to 2 dimensions. What, 28 by 28, okay. So yeah, I define t-SNE, and then you fit transform to these features, and you get MNIST, 2-dimensional vector for these 30,000 data points. So there's 30,000 images, and now MNIST gives you 30,000 by 2 matrix where the 2 dimensions are the low dimension representation. And you can see that it looks like this. So here's the first image. Here's the first dimension. X is 52, Y is 24. Target is 9. So this is the 9th. So the label is 9, right? So there's like 9 different labels in this fashion MNIST. So these are or 10 different labels, right? You have t-shirt, top, trouser, pullover, dress, coat, sandal, shirt, sneaker, bag, ankle boot. So these are the different categories that you have in this fashion MNIST data set. So the target represents to one of these, right? Okay, great. So once we have this, you can even look at the distribution here in fashion MNIST. There's kind of roughly 3,000 images per category, and there's 10 categories. So that's 30,000 images. That makes sense. So if you look at the t-SNE plot, it looks like this. And it's not completely separated like we saw for digits data set, but it's fairly doing a good job. If you look at, for instance, if you look at the brown one here, that's a trouser that stands out. The purple one is sandal, and the red one is sneaker. So sneaker and sandal are kind of partially meshed up, but they still kind of separate out for the most part. Maybe there are some sandals that look like sneakers. So those might be overlapping, right? But where you also see a lot of overlap is coat, the gray one here, the coat, that kinds of overlaps with shirt. It overlaps with pullover. It overlaps with ankle boot. I don't know why it's overlapping with ankle boot, but yeah. So this is kind of a little bit of overlap. And then you see the pink is also overlapping with blue, which is t-shirt is overlapping with shirt, which also makes sense. I mean, t-shirt, shirt, they kind of very close to each other. So you can expect some overlaps there. So t-SNE visualization gives you something like this on the MNIST. So pretty useful thing for data visualization and understanding how your data kind of softly clusters. Right. Let's jump back to uh, let's jump on a new topic. So we spoke about k-mean. So we looked at k-means, k-means plus plus. We looked at data visualization through t-SNE, and we also said that's connected to clustering, but it's a soft clustering. Then now we're jumping onto hierarchical clustering, where we fix some of the issues that k-means had because of spherical clustering, right? So let's look at hierarchical clustering. A lot of data in nature is hierarchical, right? Let's take a look at this image. For instance, if you look at, let's look at this. Let's look at mathematician, right? So Gauche was a mathematician. And then mathematician is connected to scientist. Let's look at organism. Plant is a type of organism. Person is a type of organism. Physical entity is connected to this. So this is also interesting. Animal, mammal, a specific kind of mammal, and then a sperm whale. So there's a hierarchy, right? So a lot of data has hierarchy. So you can kind of, like if you take a species of the animal kingdom, again, there is a hierarchy, right? So I think, yeah, so there's a lot of, it's not labeled here, but you can see a hierarchy in the species of animal kingdom. So there's a lot of hierarchy that happens in nature. So instead of just learning a few clusters, what if you learned a hierarchy of clusters? And the hierarchy can better help you understand the breakdown of the data, right? So that's the whole idea of hierarchical clustering. So in hierarchical clustering, you avoid choosing the number of clusters beforehand. So the K is something that you don't really choose beforehand. And dendrograms are used to visualize different granularities of clusters, right? So this is an example of a dendrogram. And you see here, these are all individual data points. And when you go up, these start to form your clusters, right? Like at this level, you have one cluster, two clusters here. Then you break it down, you get one cluster here and then one cluster here. You break it down, you get one cluster here and then one cluster here. So there is cluster within clusters. So there's a hierarchy of clusters and nested structure. So a dendrogram is essentially taking all data points and putting them into a hierarchical clusters setup. So you can go up the dendrogram and you'll find fewer clusters. You go down and you find a lot of clusters. At the very bottom, every point is its own cluster. At the very top, all the points form one cluster. So between one cluster at the very top and every point in its own cluster, you can kind of toggle with a dendrogram. And there's also hierarchy. So you can say this is also like a tree structure, right? So this dendrogram has a tree structure. You'll be able to relate this to decision trees, right? Like this, right? It's the same idea. You start here, and then you have this, right? So you can see the tree structure is showing up in the dendrogram. The dendrogram is essentially a tree, but it's a tree connected to the data points that you have. It's not a decision tree, but it's a tree to structure or order your data points. So dendrograms are really helpful with hierarchical clustering for shapes like this, right? We saw k-means clustering is spherical in nature. There is something called mixture models that are not spherical, necessarily spherical, but they're still ellipsoidal, ellipsoidal in nature. So still having this kind of a congruent shape, but then hierarchical clustering can take care of arbitrary and weird shapes like spiral clusters or donut clusters. So you can learn these clusters more easily with hierarchical clustering. There's like two kinds of hierarchical algorithms. One is divisive, which is top down, and there's agglomerative, bottom up. Okay, so we'll focus more on agglomerative today because divisive clustering, though useful, is not, though interesting, is not so much useful, especially for the weird clusters that we looked at before. So agglomerative clustering is bottom up, and it starts with each data point in its own cluster. So instead of starting at the top, you start at the bottom, right? And you start merging points and merging clusters until you think you have enough clusters. So that's the whole idea of agglomerative clustering. You start bottom and then go up, and you stop at some point, and then you end up with 10 clusters or 15 clusters or whatever, 5 clusters, right? So one example is single linkage clustering. So since we're a little bit short on time, I'll skip divisive clustering. We'll jump to agglomerative clustering. So let's look at the main algorithm here. Each point is in its own cluster to begin with, right? And you define a distance metric between clusters. So you say, okay, this is how you compute distance between two clusters. And the algorithm is very simple. While there is more than one cluster, you keep merging the two closest clusters. You keep merging until you think you should stop. Right? So in the beginning, you have n clusters because n is the number of data points. But then as you start merging, you will see there's fewer and fewer clusters. And then at some point you stop. Okay. So for instance, the first step is initialize each point in its own cluster. So you see there is a circle around every single point. So this is each point in its own cluster, right? Now we start merging. Of course, you need a distance metric between clusters. So there's distance between points. So I just want to differentiate these two. So one is distance between points. So let's call this Euclidean or whatever, Manhattan. You can have different distance. And then the second is distance between clusters. So you have to define what this is as well, right? So this is what is done here. For instance, single linkage is distance between two clusters is the minimum distance between any 2 points in the two clusters. So that is single linkage. For instance, if you look at C1 here and C2 here, this is the single linkage distance. Why? Because if you see the distance between 2 points that are actually closest to each other between C1 and C2. So that's why this is the single linkage distance between two clusters. So you have to define a distance between two clusters. Once we have the distance, you can start merging. So to begin with, each of these is its own cluster. Maybe I merge these 2 points and I get something that looks like this. I merge these two. Then maybe I still want to add one more point to this cluster, and then I get this. So this is now my new cluster. Now maybe I want to merge these two. So I get that. So I get this is one cluster and this one cluster, and everything else, all the other points are in their own cluster as well. You can see the merges are shown here in the dendrogram. So you're starting to build a dendrogram here, right? And then you can keep merging, and then this dendrogram gets more and more complicated as you keep merging. And at some point, maybe let's say you have 4 clusters after you've done this merge, 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 merge. At some point you have 4 clusters. So you can see this is 1, this is 2, this is 3, and this is 4. The 4th cluster is obviously looks more complicated because there have been a lot of merges that have happened to get to that point. But if you look at the 2nd or the 3rd cluster, they're simple. There's just 2 points that got merged. So when you look at a cluster in agglomerative clustering, it might have happened very easily, or it could have gone through a lot of steps to get to that point. Okay. And then maybe at the end you have 2 clusters. So you can see this is 1 cluster, and then this is the other cluster. So you can have like something like this. And if you go all the way to the top, then all the points are in its own cluster, and that's what this says. This all belongs to 1 cluster, right? So with agglomerative clustering, we are able to learn weirder clusters like this, right? Yeah. So another thing about the dendrogram is x-axis is the shows the data points, and y-axis shows the distance. So the height is equal to the distance between clusters. So the taller it is, the more the distance between the clusters, right? So the height represents the distance. So for instance, if you look at this height, that's the distance between the blue and the green clusters. So, you know, this distance here, what's the distance here? So if you look at single linkage, this is the single linkage distance between the blue and the green. That's what you see here as the height, right? Okay. There is something about how to stop. Maybe you can specify how do you stop merging. You can say, well, I stop when the cluster distance between any 2 merges that I can do is more than some d. So some pre-specified distance. So the distance becomes too large. I say, okay, this is where I stop. I don't want to have any between cluster distance to be larger than a certain distance. And at that point I stop, and I can threshold and I can cut it off, right? So let's do a quick in-class exercise. If we were to cut off this dendrogram on the dotted blue line, right, how many clusters would we be left with if we were to cut it off at this point? So just take a look at this and see what you get. The poll is active, so you can answer on the poll. Okay. Okay, so yeah, as we cut it here, we realize, you know, there are 5 clusters. You can see there's the on the at the bottom at the left you have the pink cluster, then you have the blue cluster, then you have the green single point cluster. So green is just a single point, its own cluster, and then you have the orange, and then you have the black. So there's 5 clusters here. Yeah, there's some hyperparameters. There's some interesting questions related to agglomerative clustering. Yeah, maybe we'll cover this in the next lecture on the hyperparameters and the types of linkages and things like that. Very exciting material. We'll get to this in the next lecture. So I'll stop here. And if you have any questions, we can discuss it. I'll be around for some time. Otherwise, have a good day.